So this is our last lesson of the semester.
Yes.
Of the semester.
Let's have a look over rate.
There we go. That's the spirit. All right. So we're going to talk about these things called linear approximations today. Let's see. Let's kind of jump in. There's not much to say here. Let's kind of develop the concept a little bit. So let's say that a bicyclist is accelerating as she coasts downhill. At t equals 0 seconds, her speed is 3 meters per second. How far will she travel from t equals 0 to t equals 1? 3? Why do we say 3? Good. So 3 meters per, is it meter? Yeah, meters. 3 meters per second, and 1 second has gone by, right?
Yes.
Do another one. How far from 0 to 2?
6.
0 to 3? Oh, 9. There we go. Jonathan's talking about it. Why is this technically not accurate?
Because we haven't accounted for that.
Because
She's going down.
really, her speed is increasing. So her speed is getting more and more over time. So she's not really going 3 meters per second over time. That's just how fast she's going at t equals 0. But by the time she gets to t equals 1, she's going faster. And by the time she gets to t equals 2, she's going even faster, and so on. Now, all of these are approximately right. Okay? Which one of these do you think is most right? Why do you think 3 is the correct one, Mateo?
Because as the time goes on, you're still coasting downhill, so you're going to go faster, faster, faster.
So in other words, on the time interval from 0 to 1, her speed is actually closer to 3 than it would be on the interval from 0 to 2.
Yes.
Because her speed is increasing more and more every time. So you're right. So good. So here's what we have from this. This is a linear function that you guys have here. A linear function is one where it increases by the same amount every time. Here's our function, y equals 3x. At 1, the answer is 3. At 2, the answer is 6. At 3, the answer is 3. That's a linear function, a straight line. But really, the bicyclist her speed is increasing. Okay, and so it's not really a linear function, but you're using a linear function to estimate. So let's kind of delve into that a little bit more. But let me ask you this. Will she have actually gone more or less than what we're estimating every time?
More.
She will always go on a little more. And why would she always be going a little bit more? Because she's speeding up, right? And because of gravity. That's a fair answer. Okay, so here's a graph of the actual position of the bicyclist, meaning this takes into account her acceleration. And you guys can see it's curved a little bit, right? And that's what happens whenever speed is changing, is you get a curve. But here's what we were thinking. We were thinking linearly. We were thinking every second, 3 meters. Every second, 3 meters. Now, how can you tell by looking at the graph if the tangent line gives us an overestimate or an underestimate of the actual y values? How can you tell if our red dotted line gives us an underestimate or an overestimate of her actual distance that she's covered? How can you tell just by looking at the graph? It's underneath of it. There you go. And well, so now let's analyze why. So this vertical axis represents her distance, right? So since the blue line is above the red line, that means the blue line is going more. So in this case, our linear function here is giving an underestimate. Now, just so you guys know, I just used the word flippantly up there, like we should have known that, but we don't. But it's actually a tangent line. Okay, it matches the speed at this point, but after that, it just kind of coasts off away from it. Let's see. Too far. What would be what would the curve of the position function look like if the tangent line were an overestimate? So in other words, the curve of the position function looks like this when it's an overestimate. I'm asking, what do you think it might look like if it were an underestimate? Does somebody want to sketch it? I don't know, I'm looking at Mateo all the time. You're my most active participant. Everybody always says stuff, mumbles, but you're always very loud and clear. Sorry I'm staring at you like you're the only one. All right. Well, I'll draw it then. Don't you guys agree that in that case, the curve of our position function, that's this person, let's say this was her position now. In that case, our tangent line would be giving us an overestimate, right? Instead of an underestimate. Okay. How would we change the story of the bicyclist so that this would be her curve? What would we say is happening here? Her speed is decreasing. Kind of maybe like she went downhill. You know, like she just finished coasting downhill, and now maybe she's just kind of coasting uphill. So it's like slow, and that's the point. So let's move on here a little bit. What is a linear approximation? When we use a tangent line, which is a linear function, to estimate the values of a function, we are making a linear approximation. So if you guys see here, I've got graphed here some curve, maybe it looks like a square root function maybe, and I've got a tangent line here. I mean, look from here to here. Aren't those lines, the straight line and the curving line, aren't they essentially identical? So you can use a linear function to estimate a curving function sometimes, right? And the closer you are to that point of tangency, the better your estimate is, the better they match. And as a matter of fact, right when you're on top of that point, they are exactly the same. They have the same slope. They have the same point. But the further away you get from it, the less accurate it is. And by the time you're out here, maybe it's not even a good estimate anymore. Okay? That's what a linear approximation is. So let's talk about these a little bit more. So the y values and the slope of the tangent line can be used to estimate the y values and slopes of a function. So if you have a really complicated looking function, but you have a nice tangent line to represent it, you can use that tangent line to estimate what its slope is and to estimate what its y values are at that point, or points close to that tangency point. The approximations are better for x values closest to the point of tangency, and they actually have the same exact y value and slope at the point of tangency. Now this is an important thing. Might want to star these on your notes. Last year, you guys should have talked about something called concavity in your pre-calculus class or in your geotrig class. Concavity refers to the curvature of a function. When a function is curving upwards, that's concave up. When it curves downwards, that's concave down. The tangent line to a concave up function is an under approximation, and the tangent line of a concave down function is an over approximation. Why? Because it's above or below, right? So if the function is concave up, then the tangent line gives an underestimate of the y values. And if the function is curving down, then the tangent line gives an overestimate of the y values. Now, I don't think the same thing applies to the slopes, though. The slopes could be different on either side, so we won't get into that. But it gives consistently those two things are true. Okay? So why do we do this? If we don't know an original function, but we do know its rate of change at a given point, then we can use linear approximations to find answers. You guys did that today. You knew that bicyclist was coasting downhill, But logically, you thought, okay, 1 second, I'm sure her speed didn't change that much. She probably went about 3 meters per second, a little bit more, right? So sometimes you don't know what the real function is, so you can use those just to estimate a ballpark answer that's good enough, right? As you know, in everyday applications of mathematics, estimations are quicker, and they're usually sufficient to give useful results. Okay, so they're usually good enough, so to speak. I've seen applications of this stuff in engineering. Anytime you're designing something, there's going to be some measurement error, right? So I've seen them use linear approximations to calculate just how bad the error is, and whether or not that's going to be an issue. I remember one time my father-in-law was helping me build a patio on my back porch, and he's good at it. And even though I'm a math teacher, I mean, that's what the guy does for a living. He's a contractor. But even though I'm a math teacher, he could do these things better than me, even though I know all about measurements and stuff. I don't know how he does it. But it's just interesting. If you're off by like a couple of degrees on how you position one of your pieces of wood, by the time you get to the end, like 20 feet down, everything's lopsided and screwed up. So it's very tender work, and that's what we call error propagation. If you have a little error at the beginning, by the time you've done a lot of things with that error, it could be a big problem. And so engineers use linear approximations to estimate error propagation and determine, is that going to be a problem or not. So back to what we're going to be asking you guys to do today. So let's go ahead and look at example 1 here. All right, so this is how the questions could be asked. They could just be asked this simply. Use a linear approximation at x equals 1 to estimate f of 2. Okay, so let me show you why we're doing this. What is f of 1 in this case? Zero. Thank you. Great. Good. It's 0. So f of 2. We're going to estimate f of 2. Okay? And we're going to do that with a tangent line. Okay? I think I'm going to... Nah, I won't cheat just yet. I don't want to show you guys the graph just yet. All right, so here's what we're going to do. To estimate what f of 2 is, and the reason we want to estimate that is because if I asked you this, you would have to either get out a calculator or give up, because we don't know what that is. What is ln of 2? There's no nice rule for that. ln of 1 is 0. We don't know what ln of 2 is. So we're going to use a tangent line to get a pretty darn close estimate, even into the decimals, of what that would be. So here's what we're going to do. The first thing we have to do is we have to find the tangent line at this point. So I'm going to use what I know about where it equals 1, and I'm going to create a tangent line there so I can estimate the original functions. Here we go. How do you find a tangent line? You need 3 things. You need an x, you need a y, and you need a slope. What's the x? What's the y? No. 0. Somebody said it out there. It's 0. When x is 1, y is 0. Now, we need a slope. How do we find our slope at that point? Derivative. That's right. F prime of x, which is what? 1. And so f prime of 1 is 1. So I've got a slope now, right? And then we write our equation. So my equation of my tangent line is going to be y minus y1 equals m times x minus x1. What's my y value? What's my slope? And what's my x value? Oh, it is 1. Okay. Okay, cool. So my tangent line, if we want to simplify this, would just be that. Now, you guys remember what f of 0 was? I'm sorry, f of 1? F of 1 was 0. Now, what's y of 1? It's 0 also, because that's where my tangent line is hitting this curving log function, and so they have the same y value and they have the same slope at that point. They both have a slope of 1 at that point, and they both have the same y value at that point. Now, as I get further and further away from x equals 1, it's not quite the same. It's a little bit off, but it'll be close, right? And 2 is not too far away from 1, so that's probably a good enough estimate. So let's do it. Use your tangent line to estimate f of 2. So here's how I'm going to write this. F of 2 is approximately going to give us the same thing as y of 2, my tangent line, which is 1. So f of 2 is going to be approximately the same thing that my tangent line would give me at 2, which is 1. Now, we're going to actually get out a calculator, and we're going to see what is ln of 2 really, okay? Because I want to show you guys just how accurate it is. Let's see. ln of 2. It's 0.693. Probably not good enough for designing things. Being off by a tenth on a measurement is not good, right? All right. The more curved a function is, by the way, I would imagine, couldn't you guys imagine it? If a function's not really very curved, tangent line's going to be really close, but the more curved it is, the quicker it's going to get away from your tangent line, right? So that's another branch of calculus. There's some calculus 3 at colleges where you can actually calculate the curvature of a function, just how curved is it. But anyway, in this case, it's 0.693. So here's my question. F of 2 equals 0.693. But my tangent line tells me it's 1. So did my tangent line give me an overestimate or an underestimate? So if my tangent line gave me an overestimate, should my function be concave up at that point or concave down? Down. All right, and I'll show you guys the graph now. So let's write that. So I don't know how much you guys want to write here, but if you want to give yourself more notes, you could say since y of 2 is greater than f of 2, f must be concave down at x equals 1. Okay. So there's the function, and I'll put the tangent line at x equals 1 up there. Uh-oh, I thought I had it. I guess I won't. Where'd it go?
How about you just draw it?
No. Actually, I think I'll have to. All right, so at my tangent line at 1 would be here, right?
Yeah.
See, that's where y equals 0. And we said it had a slope of 1 at that point. So I'm just going to make a straight line with a slope of 1 there. By the time I get to x equals 2, here's the real f value. Here's my tangent line approximation value. It's an overestimate, therefore it's curved down. Okay? And just like we predicted, since the tangent line value was greater than the function's value, that means the function must be curving downwards. It must be concave down. And that's a linear approximation. All right, here's one for you. Because I didn't change it, but it's really student practice one. So I'll put SP here. Go for it. Okay, so there's that answer. Let's look at something else now. Example 2. The line y equals negative 2x plus 18 is a linear approximation. Now, I need you guys to understand what that means, though. If I tell you that this is a linear approximation, what that means is that this is a tangent line to this function over here at x equals 4. So this is a tangent line to this function, and that's the point of tangency. You might want to label those. we're dealing with a language here. This is how mathematicians speak, okay, when we're in this kind of problem. So y equals negative 2x plus 18 is a linear approximation. That means it's the tangent line to this function at x equals 4. X equals 4 is the point of tangency. All right, so what is h of 4? Well, as you guys know, don't write this. Isn't the actual function approximately equal to the tangent line? So the value of my function at 4 should be approximately equal to my tangent line at 4, right? And my tangent line at 4, I can find that by just plugging in the 4, which is going to be negative 6 and 18 is 12. But I didn't want you guys to write that.
Wait, what?
Did I do my math wrong?
Yeah, absolutely.
It's 10? Oh, I got
You
6.
added them together.
Thank you. So 10 is good?
Yeah.
Okay. So now I asked you guys not to write this yet, and that's because there's actually something up here that's not quite right. Does somebody know what it is? It's not in the calculation. It's in the symbols. What do you guys notice about the number that I plugged in? And what's special about that? It's the point of tangency, right? What do you know about the function and the tangent line at the point of tangency? They're actually exactly the same. So what's my problem up here? We're not going to put the little wiggle signs. Since this is the point of tangency, it is equal to the tangent line value at that point because they're sharing that point. Okay? So there's that. So now you guys can write it. Little detail to watch out for there. A lot of this is just in the language. Number 2 is really just another language question. What is the instantaneous rate of change at x equals 4? So the key to answering this is understanding what instantaneous rate of change means. So what is meant by the phrase instantaneous rate of change? Slope. Slope. Good. It's the slope. So what is the slope at 4? No. Negative 2. Right? So here's the deal. This is my tangent line, right? This is my tangent line of this function at x equals 4. And at x equals 4, they have the same exact slope. So the slope of my function h at 4 is the same thing as the slope of my tangent line at x equals 4. And the slope of my tangent line is negative 2. All right. If this were an FRQ, you should not write m equals negative 2 because you're inventing a new letter. And you're not supposed to do that unless you define it. But I'm being lazy here. So if the line y equals negative 5x plus 30, this is a tough question, I think. If the line y equals negative 5x plus 30 is the linear approximation at x equals 5, is concave up or down on the interval from 4 to 5? So this is a tough question. It's meant to make you scratch your head and think. Why don't we brainstorm this for a minute? So here's what we know. We know that at 4, that's my tangent line. But now they're telling me at 5, that's my new tangent line. So what's going on with that function from 4 to 5? That's what the question's asking. Is it concave up or down, and why? Yes. Okay, so let's visualize this a little bit. We have a graph, right? We have something going on at 4. We also have something going on at 5. At 4, let's say I got a point here. And at 5, let's say I have a point right here. I don't know if this is going to work. Let me think. Why not? Why? Okay, good. So how do you know it's decreasing, Matthew? What do you mean plug it in? You get what? Okay, good. So he actually did some math here. So when we plugged in 4, we get 10. And then when we plugged in 5, he got 5? Now, it's possible, though, for a function to be curving up here, isn't it? Technically. But it could also be doing this. So we don't really know the concavity just because it went from higher to lower. But what did we know? What about the slope? My first slope was what? -2. What was my next slope? What would that look like? Now you can tell, right? That's a hard question, but I think it's a good one because it makes you think a lot about the concept we're talking about. So we're going from here to here, thanks to Matt. We know those points. And then also looking at our slopes, it goes from steep downward to even more downward. It's got to be curving down. And therefore, we can say that it's concave down. So that's a tough question, but a lot to think about. Good stuff. Would these tangent lines give over approximations or under them? Since they're on top of the curve, my tangent lines would be giving me over approximations. Okay, so you guys try this. Now, this is not like the last problem. You have to think about this to answer it, okay? There's some things from the last problem in here, though. But read it, think about it, figure it out. I'll give you a couple of seconds. So, good question. I like that question. All right. Well, with the time that remains, I'd like to maybe practice a little bit more with you guys. Why don't we do some homework, huh? Want to get out a piece of paper to do your homework? Because when we did example 1 today, I was a little bit insecure with the comfort level that I saw. So, I don't know if you guys can see that okay or not. I'll read it to you, though. It says, let f of x equal sine x. So we have f of x is equal to sine x. We want to use a linear approximation at 0 to estimate f of 1. Okay? So, Walter, if I want to use a linear estimation from x equals 0 to approximate f of 1, what do I need to do first? Okay, so what we need to do first is we need to find the linear approximation. In other words, we need to find the tangent line. Okay, so Mateo, what do I need if I want to find a tangent line? Okay, we need a slope. What else? All right, guys, so at this point, just shout out, I guess, what is the x value? How do I find the y value? Plug in 0. What is sine of 0? It's 0. Cosine of 0 is 1. What is, now how can I find my slope? Derivative. And then we plug in 0, which is, now we got 1, right? So what would my tangent line be? Which would just be y equals x, right? So there's my tangent line. Now, I still haven't answered the question yet. The question said, use f of x equals, if f of x equals sine x, use a linear approximation at x equals 0. So that's what this is. That's my linear approximation, x equals 0, to approximate what f of 1 is. How do I find out, how can I estimate what f of 1 is? Plug it into what? We're estimating, because we don't, does anyone here know what sine of 1 is? There's no answer for that, right? We would have to have a calculator. So we're going to use our tangent line. So f of 1 is approximately the same thing as y of 1. And what is y of 1? 1. Okay? So that means that sine of 1,
0.017.
what is it?
0.017.
That we are very far off, aren't we? That's interesting. I wonder if we've done something wrong here. That's too far off. I mean, it just might be a really bad approximation.
It's horrible.
Well, let's see. Oh, I think I know why. Yeah, that makes sense actually. So there's that. It's a terrible approximation. But let's leave it at that's what it is. So what it was what 0. What?
0.
Like that? And did you guys know in calculus on your FRQs you're supposed to round to the third decimal place? I need to start saying that more often. I was much better about that last year. 0. What?
0.0. Oh, it was 0.017.
Like this?
Yeah.
Okay. You want to round to your third decimal place, just so you guys know. They're picky about that. All right. So based on our answer to part A and B, would this be concave up or down? It would be down because my tangent line is higher than my curve. All right, guys. I'll see you mañana.